So I'm Tamás Varga. I'm together with Billy here. We are responsible for the XCT data generation and analysis. And before our main event, which is Maruti's presentation, I'll just take a few minutes to overview or review what was covered in the first working group meeting that took place recently. So I'll just give an overview of the MONet XCT data types again, then go through a few slides of topics of the last meeting I mentioned, and then mention the GitHub page where this information can be looked at. So for the MONet cores, we collect 2 lower resolution scans and 2 higher resolution ones. This slide shows the kind of this lower resolution scoping scan where we collect this image on the whole core in 2 tiles that are stitched together, and this gives you a nice image of the overall core, the soil heterogeneity. This is a cross section of the middle of the core, I mean half of the core, and but we did not perform the pore network analysis on this data. We do that on these higher resolution scans, which is shown on the right here. We collect 2 of those, both from the top and bottom half, and we zoom it in as much as possible for the core diameter. So the previous scans are just called top and bottom, top bot in the file name. These are called the top zoom, bottom zoom scans, and this gives us enough resolution, about twice as good resolution as the previous slide scans, to basically perform the porosity analysis, segment the porosity, visualize it, derive the numerical numbers, and do pore network analysis as shown here. In terms of the data we provide, and here I'm using some of the cool images of that Billy created, or videos. So we provide both image data and numerical data, images of the whole core, that's a merged data set. And then this sub-volume that I mentioned, we collect 2 of those to do the porosity analysis, where we can visualize and show the total porosity. Then the top image here is the connected pores, and below is the isolated or unconnected pores. And then we perform the pore network modeling on this. And new is that we include a binary image stack of the segmented porosity, all 3, total, connected, unconnected, that you can actually visualize on your own computer. So I also mentioned that how that can be done, and happy to help with that. Mentioned it in the last meeting. And this is the numerical data that both I and Billy talked about, that you can find, and I'll show it in a minute, in the spreadsheet that is uploaded. And this is it. So Billy created this guide, the spreadsheet that you find for each high resolution kind of half core analysis, contains the scan information, all the pore parameters, bulk density estimated from the image data, and the flow and transport parameters that we also calculate based on image data. And I also happen to have a slide on the Science Central link that Odetta and Vanessa mentioned. So currently you can look up FTICR and other chemical info based on the map, and first the CT data will be downloadable, and then later it will become also searchable to try this tool, but not yet. And then this is the GitHub where people can look at all the materials, slides, information covered in these working group meetings, and we are on the second one right now. And there's the link. You will also have these slides uploaded there. So in addition to the data types, last time we gave a brief intro to XCT, the method, and I just talked about the basically the scanning workflow and the data types. And then we also talked about other data types, not included in the upload, but what we can provide. So if you're not familiar with XCT, please check out the slides from the last meeting. I'm not going to go into it now. And then this is just a slide about the 4 scans shown in these the red tiles that I just mentioned. And as far as other images or other data types are concerned, we can create animations from the data that is available. The data can be converted into a mesh that can be used for simulations, for example. The segmented porosity can be converted into an STL format for also modeling or 3D printing, and other numerical information such as pore throats, pore coordination numbers can be derived as well from the data. And here's our fantastic MONet team. And with that, I'd like to hand it over to Maruti for his part of the presentation of applications of CT data for simulations and modeling purposes. Stop sharing.
Thanks a lot, Thomas. So let me share my screen.
Cool. Thanks.
Any questions before we move on?
You're happy to answer a few questions now or after the Maruti's presentation.
Okay, can all see my screen?
Yes, but not in presenter mode yet.
Oh,
I don't know if
okay.
it's on purpose.
Yeah, sorry. I put that on purpose. The reason is that I'll lose you all if I put it in presenter mode. I'll not be able to share multiple screens as I show some demos. If that is okay, Vanessa.
Yes, that's okay. I just wanted to
Okay.
make sure you were aware.
Sure. Okay. So hope you all can see my slides. So today we'll be talking about model data experiment integration workflows that we have been developing for users and their capabilities, focusing primarily on the XCT data. And we also will show some initial preliminary results of how we incorporate SEM EDX towards the modeling. And before we go, okay, let me quickly share some links so that everyone will be able to do these things as we where is the chat button here, so that everybody will be able to access these. Come on. Okay, so today how are we using these workflows and what are the use cases for modeling and data analysis? So we'll get started, like what are the questions we would like to answer. Primarily using the XCT data and how we can use that in your MONet workflows. Come on, what happened? How to access this data and primarily like some ways to do some programming primarily through Google Colab. And if you have access to EMSL Tahoma, you can use the Jupyter Hub and the Jupyter Notebooks there for the users there, and how we can access the data also from the EMSL MONet computing GitHub. And then we'll talk about the use cases, primarily the XCT segmentation, how we can differentiate between a solid and a pore, what type of pores are there, the corresponding connectivity, visualize these things in a 3D setting, which is needed for downstream modeling pipelines using a software called Paraview, and have a way to construct a mesh for that for the modeling purposes, because we need a mesh. By mesh, we mean we are dividing this entire soil core into smaller blocks so that we can see how the flow happens within these smaller blocks. So how do we construct a mesh for downstream modeling pipelines? And what is a modeling software used? That is primarily pFlowTran, focusing on carbon degradation. So I'll show you some simple scripts, what a typical input deck looks like for a batch reactor and how we extend that to 3D models to construct a complex input deck. And once you construct a complex input deck, what is the way for model experiment data integration, and some AI workflows that are available for users as part from the EMSL Tahoma, which still currently under progress, and some use cases of how these components are being used for sensitivity analysis, and some advanced data analysis that is available primarily to HPC Tahoma, because these are all computationally intensive modeling efforts. So how do we tune such models on HPC? So, but primarily it will be hands-on as I show some demos, and you can also do it on your own as we go through, but it should be straightforward to do that. And stop me if you have any questions. So the key takeaways from what we have today is the following. So we want to answer these three questions. So how do you want to use the EMSL MONet data, primarily the XCT data or other types of data sets that you'll be getting over the time within the modeling workflows? For example, you have XCT core segmentation data. How do you use that in an open source context, visualizing 3D data, segmenting that data set, and how do we construct a typical mesh for downstream modeling pipelines? What is a process to run pfloat, what are the resources you can get by contacting us? What goes into a typical pfloat workflow, and what type of data you can ingest? For example, 3D data from XCT, and down the lane when you have some chemical information data, you can also incorporate that. How do you visualize those data sets? And how do you incorporate hydraulic experiments once you get on a core? How do you use that information for calibrating your process models? So what I put in your chat is the resources for accessing some toy data sets, images. It's going to be the same for whatever data you're going to receive, the notebooks, which can be repurposed for your needs, and sample output so that you can visualize and see data sets. So this includes the EMSL MONet working group XCT GitHub link, along with visualizing data. So you can download this open source ParaView software, and a very simple Google Colab notebook for a sub volume of a XCT 3D XCT image, and a full volume of that is in a associated notebooks that you can access through this. And yes, yeah, Vanessa, that's right. If you're interested in applying these tools, yeah, I'll be describing over these slides, and I'll make these slides available through the EMSL Computing GitHub. That's correct. And if you need help on EMSL Computing, how to use EMSL Computing resources, I'm always available to help, and please shoot me an email, or Vanessa or Thomas or Odetta, they can forward me that they can forward that information. But my email is listed below in the first slide. Okay, so let's get started. So Google Colab and Jupyter Hub are primarily some notebooks that will allow us to have some exploratory data analysis, and an open source way for people to analyze and use these data. So these are primarily use Python as a basis for analyzing the data. And Jupyter Hub is very similar to using Google Colab notebooks, which I'll be showing you in a short while. And it's an interactive environment for writing scripts, visualizing simple plots, and data analytics. And you can share the code with whoever you want. And if you have a Gmail, it's primarily you can access those notebooks and play with it directly with your Google Drive. And this is not what I'm going to show is not heavy, but a heavy intensive part is in the EMSL Computing GitHub. You can access a much more intensive way to do this analysis through Tahoma, primarily through the Jupyter Hub Open on Demand, and that is the Open on Demand OOD process. And if you have questions, always MSA Computing and user community is available to help you out. Okay, so a typical access to Tahoma is like primarily through a GUI. So you, the EMSL users have an account, and you can use that account to request the total number of hours, how many nodes you want to work, do your analysis. And once you start, typically it is queued. And once it is queued, you'll be able to run. And once you run, you'll have like a GUI to understand these notebooks and follow a step-by-step process. So what a typical Jupyter Hub and the corresponding Google Colab notebook. Today, what I'll be showing you is this. How do we access that and how do we play with it? So this is a snapshot of what I have created for you all, analyzing a simple XCT subvolume data set, which is highly porous, and it should be the same for the MONet data you'll be seeing. So the analysis is straightforward. You can modify certain links here and do the same. So let me walk to the step-by-step. And oh yeah, one question. Is there an RStudio workflow as well, or with XCT data is Python better? I'm not that familiar with RStudio. So typically Python is way easier to analyze data because you have a lot of open source libraries and there's a considerable support to analyze these data, and makes it much more easier for people to access and collaborate. I'm not that of an R user, so I don't have an RStudio workflow here. Hope that answers your question, Cassandra. Okay. Okay, thanks. Okay. So the link I have shared in the folder is this XCT folder. And there's an extensive README here, and I updated certain parts. And you should have access to this through the EMSL Computing GitHub if you have a GitHub account. And there are various data sets here. You have images and a sample soil porosity data, how the porosity looks like. And I have curated some data for you from the subvolume image and how to visualize that through a file that we output called VTK Visualization Toolkit. And I'm going to show you how to do that, how to play with that big set of data files through an open source software called Paraview, and extensive like 2 different notebooks, primarily subvolume and full data analysis, along with a detailed hands-on tutorial. So in this README Markdown, you should have a link here. I put that link in the chat. So when you click on this link, you'll be opening this notebook. Can everyone see this? Let me zoom this in a bit. So Tomas, can you see this, right?
Yes, we can see it all right. Yeah.
Awesome. Okay. So this is a typical Google Colab notebook, and Jupyter Notebook is also very similar to this. So in this, what you'll see is like all these buttons, the file edit, insert, and runtime. First, you want to make sure your runtime is connected. So when you click on runtime, what you should see is like these various options. And when you have runtime, let me interrupt this. So restart, interrupt execution, and runtime. So restart session here. So when you restart a session, it will clear all the input variables that you see here. So that's a runtime state, including all the local variables are lost. So once you do that, so you should see all these empty cells. Okay. So once you see all these empty cells, then you can start playing with this notebook. You should also see something like RAM disconnected, like RAM and disk are connected. So it says when you hover onto that, you should be able to see connected to a Python 3 computing engine backend, and how much amount of RAM it is currently consuming and how much is available. So with whatever data set we have, it is sufficient for us to load into a memory that is available through this Google Colab notebook. Okay, and you have a set of buttons here for you to help it out, but this is the main one. So when I click on this, I will know what are all my files here. So this is a typical Google Drive node folder, and when you refresh it, you'll see how much disk space is available, what are all the folders here. So this is just my sample data, what it looks like. I was playing with some other things so that you can see what a typical folder structure looks like. And there should be nothing here when you start working on your workflow. And I'll just click off here so that I can go through step-by-step process and we can run it simultaneously. So the first here, the Google Colab notebook is organized into cells. So we have code cells here. So when you click on this, you'll insert a code cell. So I have inserted various code cells. And when you want to insert a text, you can add a text here. Okay. So I have inserted various code cells that will allow you to understand and analyze these text. So these are currently populated because I ran that so that you can understand what exactly is going on here. Okay. And any questions so far? I don't see anything there. Okay, let me run this. So what I'm doing to the first one is I'm removing anything that already exists in my folder. So when I run here, you should be able to see this is executed in a microsecond. And what I'm trying to do next is importing various modules from a computer vision for segmentation of an XCT data and plotting modules and time modules. Okay. So once I do that, it should run, it should import all the modules and the corresponding files. And the next step is I'm trying to clone from the GitHub what exactly is the corresponding data set. So when I run this, it should run that cell. It is cloning in the sense like you're trying to download the data and corresponding images, and your file structure should be available to see this through this file folder. So when I click here and refresh it, you should be able to see the toy data set here. So whenever you have a MONet sample, you can just copy paste here, or again, put it in a GitHub and edit this line. You should be able to see that. So once you do that, so I have written some function files here to visualize that. So BTK is a visualization toolkit that is available through Paraview, and which I'll be showing you next. So I have created some functions wherein which I want to visualize how this data looks like for a p-flow-tran modeling, for a flow transport and the corresponding energy balance. So there are various parts of the element. So how we create a mesh, what type of data structure we want to write, how do we create an unstructured grid, what type of permeability, porosity, or various types of material ID, whether a typical cell or whether a typical pixel is a 3D pixel, is a pore space or a solid matrix. Those are the things that are populated here. So you run this part, you are loading this function. So just run this for now. And what I do here is next I curated a subvolume for the image analysis and the corresponding segmentation. So I use the raw XCT data that is a set of images. I took a subvolume of that and I'm trying to load that in an efficient way. So this subvolume size is by 50 by 50 by 50 pixels. So once I do that, what I'm doing is I'm loading from the corresponding file directory that is available here. So in the XCT toy sample data, I have the subvolume. I'm trying to import that. So once I import that, I'm creating a folder to binarize it. So what I'm trying to do here is I'm trying to segment the XCT image into pores and solids as a first step. You can have advanced machine learning algorithms or advanced algorithms to do that. I'm using a simple first order computer vision algorithm to get a much better understanding of how we can do a segmentation. So I'm creating a directory. Once I create a directory here, you should be able to see that. And you should be able to see the image subvolume directory. So once you do that, you load the corresponding data files, the corresponding paths, you create a mesh. So here, my smaller subvolume has each of the pixel is in the order of micrometers. So that is what I'm trying to do. I'm dividing this entire 3D volume of images into smaller pixels, and each of the pixel is in the order of 10⁻⁶ meters. So once I do that, I have written some codes here to construct the mesh and needed for the pFloatran modeling. So that is what you run here. So it should take a couple of microseconds to run. I created the mesh and the corresponding infrastructure. So here, this is where the image segmentation happens. So we have a preliminary k-means clustering, the first order ML thresholding. What I did was I loaded this image stack. And once I loaded this image stack, I created a variable called thresholding stack. So I'm thresholding in such a way that I have black and white, black pixels representing a solid and white pixels representing a pore space. So I'm constructing the infrastructure from the computer vision to read the data and organize the data and do the corresponding thresholding. So yes, the images will be considerably be noisy. So I use a Gaussian filtering and thresholding to blur the image and extract the better information from that. So when you run that, it's going to take a couple of seconds. And what it's trying to do is going to the image stack step by step, segmenting that images and creating a volume that can be used for downstream machine learning or for modeling pipelines. So just in a couple of seconds, you're able to do that. And once you do that, I created this part where in which you can visualize the corresponding outputs. So when I ran this previous cell, you should be able to see in this image binary stack all the images that are stored here. You can click on an image and see how an image looks like, but I'll be showing you in a 3D context how to load that. Okay. So once you do that, you can always visualize what a raw image looks like and what a corresponding pore space looks like. So the solids are typically what we assume right now for solids, and the white as the pores. So once you do that, you can see how the pores are being connected from one side to another side. That's where the flow happens. Now we are dividing this image into blocks so that we can visualize what's happening in this XCT. And if you have chemical imaging data, we can see what is in the pores and what is in the solids. And so once I run this, I can see how an image looks like. Finally, I want to see this in a 3D context of visualization toolkit. And I run this part here. So when I run this part, it is going to create this .vtk file. And if you go here into the image binary v3, you should be able to see this .visualization toolkit file. Now I have already downloaded that, and I'll be showing you how to visualize a 3D structure with the corresponding mesh that goes into a downstream pFloatran modeling pipeline. Before I load that, any questions? Okay, so I have already installed this visualization software called Paraview. It's free. Doesn't take much of time for you to download and load. It's less than 1 GB or so. So it's just trying to load. Bear with me while I do that. And so yes. So when you open this up, this is how it looks. So you close it. So this is a GUI. And once you have that, I have loaded this. So this is the threshold 3D file, version 3 VTK file. I loaded that part, and once I do that, you can hit an apply button here. And once you apply here, you can see the 3D image here. So there are some options here to see how the axis grid looks like. So how much, what's the typical dimension of this subvolume? What does each and every cell looks like? So this is what I'm renaming here is like a material ID. So don't worry about this for right now. And let me change some coloring scheme so that you can see what exactly is going on here. Okay. So the solid represents here what we assume is the like the black color represents what we assume to be a solid, and white is the pore space. And this is how a 3D image looks like. And if you go into surface with edges, the mesh I have created is represented in these voxels or these mesh cells or these pixels. Now, if I click on this and rotate it, I can see how the 3D mesh looks like, what a typical 3D mesh looks like, and how it goes into a pre-flow-tran modeling, which I'll be showing a input deck in the next set of demos. So this is what you can play with it and see how a pore space looks like. And what also you can do is you can threshold it. So if I put a if I click on this and click a threshold here, the threshold button here, then you can add, for example, I can see a solid. So if I want to see the pore space, what a pore space typically looks like. So the black is the solid, white is the pore space. So I just threshold it with the upper level. So let me put some number here, 10. So once I apply here, I can see this is the corresponding solids. Let me see if I'm making that right. Bear with me. Yes, so this is the pore space. So you can see how the pores are being connected from one side to the other side. And you can see surface with edges, how it is being meshed. So this typically goes into a high resolution fluid flow simulation such as open foam, or the entire stuff goes into the corresponding p-flow modeling simulations, wherein which you can do the flow, carbon degradation, transport. So for a batch reactor, we don't need to mesh any of these. It's just one simple set of batch reactions that you want to do. But if you want to understand how we flush out minerals or carbon within the pores, or how the mineral solid matrix interacts with the pore space and the minerals, we need to do this part. So that's the complex workflows that will be available over the MONet program to the EMSL users. So you can drag drop and see how the mesh cells looks like, how you can visualize these and interact with in a typical visualization software, which is needed for p-flow-tran modeling. So before I move forward, any questions on this? Yes, I think Vanessa put the visualization software here. Okay. Okay, so I'll minimize this. Okay, maybe also let me show what a typical chemical imaging file looks like. So here I have XCT data, and I have constructed the solid and pores. If I want to paint this or color this with a typical mineral, for example, silica, how does that look like? So I have incorporated that chemical imaging data as a first step. So I drag drop that chemical imaging file. This is not available to the users yet because we're still working on testing certain things. So let me apply here and go to rescale and change the color to all. Then go to the hot red. Sorry. This. Okay. Sorry, bear with me. I'm picking a different color map. Let me pick something.
Maruti, you also have a question in the chat when you get a chance.
Okay. Yeah, sorry, 1 second. Let me close this and reopen this so that I don't mess up certain things. Okay, while it goes, is 10 a good number, or would you need to play with that at bit? Oh, 10. Okay, that's a good question. So, okay, let me tell. So I'm dividing solids and I'm segmenting the XCT. So XCT image goes, a grayscale image typically goes from 0 to 255, a discrete number. So it's 0, 1, 2, 3, 4 until 255. So what I'm trying to do is cluster them into pores and non-pores. And when I cluster them and segment them, so a solid is represented by 255 and a a port is represented by 0. When I'm trying to threshold, I'm just putting an arbitrary number that is below 255. So if you even put like 240, like 254 or 250, it should work. This is just an arbitrary number 10 that I put. You can play with whatever the number, the result would be the same. Hope that answers your questions, Rachel. Okay. Oh, okay. Thanks. Okay. So let me put that. So I'm loading the chemical imaging file here, and let me put, okay. Why is this? Okay. So I know like this part is a solid, the red one is a solid, and the other colors are how the normalized silica concentration is spread within these, or a chemical, whatever it is, how it is spread within these pores. So when I'm trying to do a certain experiment, how do I flush these out? So those are the things, those are the questions you can answer. Hey, what is my initial condition? Um, like from combining multimodal data sets, for example, XCT, SEM, EDX, or any other thing. How do I put that into typical modeling workflow? So for putting in the typical modeling workflow, I need to have initial condition. By initial condition, I mean, what is the typical distribution of a chemical in the pores and in the solids? And once I have that, then I can use that as a basis for understanding how that chemicals are being flushed out, or how a carbon degrades, or how a specific mineral is being dissolved or precipitated onto a solid matrix, or how it is being carried over when you're trying to do a flow experiments, what is being retained. So there are various interesting questions you can answer. We are aiming to answer those questions. That's the reason why we are trying to develop this capability. So that is still in a very preliminary stage, as we are trying to test other workflows, but there's nothing in the modeling workflow that you need to change. There are certain input card decks that you need to change. That capability will also be available for the users. So this is how a typical um, a chemical imaging work file looks like, and you can also mesh this up in a high resolution way and see how in each and every pixel, or in each and every 3D pixel, how a typical situation looks like. Okay, so with that, if there are no questions, I'll move forward. Okay. So I've been talking about pFlowTran. What is pFlowTran? So pFlowTran is a open source software developed by multiple national labs, primarily funded by the DOE program. And it's a multi-physics code that allows you to solve for flow, reactive transport, describing the subsurface processes. And it's massively parallel in the sense, like, so a typical XCT core, the thing that we are analyzing has hundreds of millions of mesh cells. If we want to resolve it, by resolving in the sense, like, we want to resolve it at a micro level, sorry, yes, at a micro level. And how do we resolve that? How do we extract that information? So pFlowTran has that high performance computing capability to analyze that on HPC systems like Tahoma. That's the advantage of using pFlowTran. It gives the capability to write like cards or decks of cards, so that you can understand how a typical modeling degradation workflow looks like. So you can start with a simple batch reactor, for example, in a breakthrough experiment, or you're doing a batch reactor experiment. You want to understand how a carbon degrades and what is the amount of degradation, what type of information you get. So the decks are very simple, which I'll be showing you, and you can model that type of information. So let me quickly show you that. So, oh, I already have it here. Okay, so this is a typical, hope everyone can see my screen. I still.
Yes, the
Oh, okay.
terminal.
Awesome. Yes. Okay. So this is a typical input deck. So what I'm trying to understand is like, I want to understand carbon degradation, how a simple carbon degradation happens. What type of p floatan input decks can you create, and how do we like start simple and how we complicate that? Like complicate in the sense, how do you develop a complex input decks? So here, I can do multiple realizations. We have a set of Python scripts and programming interfaces to do that. That is a capability I have developed. So if a user is interested in that, I can point them to that directions. And if you have access to Tahoma, you'll be able to do that. So a typical simulation process looks like the following. So these lines are all card text. By card, we mean like we add capabilities. Say, I want to do a simulation. I want to do a subsurface simulation with flow and transport. What type of information I add here? So next, I want to describe what is my initial condition. So I put some constraint cards on the chemical species. So the more species you have, the more chemical information you can add, whether it is mobile, a primary species, a secondary species, you can add that information. And that is in the chemistry card. So you can add the corresponding reaction sandbox side. By reaction sandbox in the sense like you can add your own complex chemical reactions, whether it's an aqueous species reaction or type of constants like parameters, the corresponding databases for the reaction networks, what type of activity coefficients, like typical aspects related to a model reaction. So you can add that in this chemistry input deck. What type of numerical methods one can use to solve this. So as this is a nonlinear system and a complex system, we need some numerical methods to solve this. There are no analytical solutions as you have complex reactions. So we provide a series of solvers to help us solve this fast. And since this is a batch reaction, we only have one cell. So we do that. But if you have I'll show you how a complex deck looks like. That is what we are constructing for the chemical imaging. So if your complex deck will add that grid information, whatever I've been showing in ParaView comes this information here. And then you provide the fluid properties, the rock properties or the soil properties here. And if you have an experiment that you measure a certain concentration of a chemical species or a fluid of a chemical species, you can output it here in a periodic observation time step, or you can add your own time steps, whether it's a day, unit, or hours, and how much time. So here I had to use typically a week for a batch reaction, but you can incorporate whatever time steps you want, whatever the final time it is, how you want to march over time, at what specific points you want to save the data. And you define a region. Like for instance, I have pore space. I want to define certain things in the pore space. I want to define certain things in the solid matrix. You can define in this regions block. I create an observation points so that, for example, you're trying to sample certain regions well. So you want to create some observation points within which you can sample the data, corresponding transport conditions. How do we all couple that with an initial condition? As I was saying, for a chemical imaging, you want to understand how each of those chemicals are spread within the entire 3D block. We can incorporate that here. So this is a typical standard input deck, a smaller set of input deck to do a batch reaction. Once we construct this input decks, these typically are available. We are able to help you on this as you have various needs for the incorporating XCT or a batch reactions or the type of information as you get from MONet. And once you created that input deck, so it's very easy to run the corresponding what is it? A p floatan simulation. So let me run that one for here. Sorry, bear with me. Okay, so these the slide number 2 I was showing you here. Did I put that one here? Yes. So this is the slide in which you load set of modules and Tahoma export. These are all the things that are already available. You don't need to do anything. So we have those shell scripts. So let me show you here. So when you have these shell scripts, so you can load these data sets, and let's say I'll just copy paste this. So when I copy paste that, I have loaded that, and now I'll run this. So typically you submit a job, it just gives some CUDA warning messages, but it runs very fast. For a batch reaction, it runs very fast. I'm able to run one realization like in a couple of microseconds. So that's how fast it is. So you can run tens and thousands of realizations and see how a typical plot looks like. I'm going to show you some results, and an output is like this. So so you save the data for various chemical species over time, like this. So you have time, aqueous species, concentration of each of those species at observation points. This column first represents the time. You have the chemical concentrations over time. This is the type of information as a text file you have, or other data formats. We have Python scripts to read this and show some nice, interesting plots. So let me go into that. So this is the capability we have been developing for the users, and to make users' life easy, so that when they bring their own data, how we construct input decks, how we make this manageable for running modeling simulations on HPC systems like Tahoma. So what does a typical process model looks like? What type of first order equations you're trying to solve? When you have flow and transport, you're going to add a bunch of terms related to flow, advection, and transport. Those are the specific aspects we have that capability on. And once you have that, you load certain modules that are already available on Tahoma and run those specific aspects. So for more complex reactions, we also have capabilities. So if, for example, you want to understand more than 10 reactions, like say 50 reactions, there's a way to do that. And Reaction Sandbox provide that information, and there are various resources that are available for people to ask questions. So let me copy paste this. That makes it a bit easier for people to have that. And the coding is much lesser within the context I've been showing. Most of these resources are available for the users through Jupyter notebooks, through input decks, through shell scripts. So once you have access to Tahoma, you go to a Jupyter lab and open on demand. It's like accessing your desktop, and you have a bunch of clicks that you can play with it and understand what exactly is going on with a set of examples and repurpose it for your own use cases. So what type of AI methodologies are available for the workflow users? So typically we have constructed process models within the modeling software called pflowtran, generate some synthetic data, use this synthetic data to do some sensitivity analysis. That is very important because you want to see which parameters are most important and calibrate them very well, and use AI models to better calibrate them, compare them with the ground truth, and reiterate it. This is what is a typical MONeX workflow is interested in. So once we have that, so this is as I've said, like we have a bunch of realizations. You want to compare them and see what is the best curve methodology. So these are the various steps that are available for a MONeT user. What are the specific observational data? How do you generate data sets, perform sensitivity analysis, and parameter estimation? Once we have that, we also have other data capabilities. What the bottom line upfront is, we also have AI modeling capabilities available for the users. For example, a traditional random forest model or a deep neural network doing parameter tuning on the scale. Those are the capabilities that are typically available for the user. So the capabilities that we have developed, for example, can be applied for other data sets as well. Say, for example, a part of the workflow users were interested in applying for FTIC or mass spec, and how we can use that information for doing sensitivity analysis. So this is already available in GitHub, and people can use it or repurpose it for their own analysis. And in addition to that, so as I've shown you, like this is the first step we are trying to do, combining XCT with SEM EDX to better understand the pore chemistry and the chemical data information. What I have shown you today is you have a typical image to the Google Colab notebook. How do we segment it? How do we assign material properties such as permeability and porosity? Once you do that, you have pre-Fortran capabilities to solve flow, reactive transport, energy balance, carbon degradation on this mesh. And once you have that, what a typical input data looks like. Once you have a standard input data look, how does it look like, and use it for visualization as initial condition. And a complex data, let me give you a show of what a complex data looks like. Sorry, complex input deck looks like. So you define various cards for simulation for flow, transport. If you want to have geophysics, you can add that. You can add various types of restart files, transport, what a mesh looks like. Here I have closer to 8.5 million cells. You can add the permeability field, the porosity field, the pore space field. You can add that information here. The material property, the corresponding permeability characteristics and porosity characteristics, the liquid pressure, what type of solvers you want to do, like how do you impose the boundary conditions and initial conditions, and locations of observation points. And you can construct a complex input deck. I constructed this through using a Python notebook, not by adding all these things. So we have that capability for users down the lane for using XCT plus potentially SEM EDX for understanding flow and transport, which is still in the very crude and preliminary stages. So with that, any questions?
Great. Thank you, Maruti. And just so everyone knows, I'll have Maruti's presentation in the link for the GitHub. And then I'll talk to him to see if we can also upload some of the scripts that he run through in there.
Yeah,
Are
I
there?
think the Python
Yeah.
scripts, all those are available. I'll make them available. The input decks are available on Tahoma, but it's still in the development stages. So bear with me as I make sure that it is quality controlled. If a user is very interested, I can help them out. It should be easy to contact, but it might take a bit of time.